Hello, let's create life. Again, but this time much bigger. I am, of course, talking about Conway's Game of Life, a topic we've covered before on the channel, and we'll have a look at that later. I've always liked the Game of Life. Here is an R-pentomino shape, and if I start the simulation, we can see that it evolves and fluctuates and moves around. It's really quite beautiful. We've got things that move, things that grow, things that die. And this is an algorithm that's fascinated computer scientists for a long time. Look at that, it's sent out these little streamers, and they're going out into the void until they encounter something else. You can see we've got some simulation going on here as well. At any point I can sort of disrupt the simulation by stimulating it. And I can right-click with my mouse to place a whole load of random cells too. It's a nice way to draw things. Now, the previous video I did on cellular automata, and specifically the Game of Life, was limited to a reasonably small size. So I thought, wouldn't it be more interesting if we had a really huge cellular automata universe going on? So this is a real Game of Life simulation, all happening in real time, and I can interact with any part of it. Now, as I zoom out, you'll be able to see less and less of it in the YouTube video, I'm sure. But when I say big, I don't just mean big, I mean really big. So let's keep zooming out and having a look at how many cells we've got now. There's probably quite a few million cells being simulated. And I don't mean, well, really big. I mean really big. Let's keep zooming out now. Oh, here we go. So we've got some more simulation going on over here. Now, this was literally millions, if not billions, of cells away. These ones look quite symmetrical, and that's quite nice, because if I simulate a bunch like that, this is all random, you just get this random effect. But if I pause the simulation and fill in a whole square like this, look at this, this is beautiful. We get this beautiful symmetrical growth pattern going on. I really like this. And eventually this pattern sends out some streamers into the distance. Oh, there they go. Off we go into the diagonals, and they're just going to swim off into the void, as these ones have done already. Let's have a quick look at these and zoom right in on one of them. There they go, they're off to discover something else in their universe. The entire size of the universe in this simulation is theoretically infinite, and this is a considerably different approach to implementing cellular automata than I've shown in the previous video many hundreds of years ago. Let's take a quick look at that.
Hello, this week I created artificial life. At the command prompt, of course.
Look at this handsome chap. Ah, the old studio, I miss you. If you're completely unfamiliar with the Game of Life and cellular automata, it's worth watching this quick 15-minute video. The rules still apply, and I'm not changing anything here, and I've no intention of repeating these rules for this video. It used a precursor to the OLC pixel game engine called the OLC console game engine. It was pretty much the same thing, except it did everything in a command prompt. I think the first thing we're going to need to do is very quickly update the code. Who was that guy? He didn't even have any grey hair. How can he possibly know anything about programming? If you hop on over to the One Lone Coder GitHub, you can go to the console game engine section and look at the smaller projects for the entire implementation of the Game of Life in that video. It wasn't a very long implementation, just a couple of hundred lines. I'm going to copy that code and paste it into a new Visual Studio project. I've pasted in the original code. I've now told it to include the pixel game engine instead of the console game engine. Naturally, I inherit from the pixel game engine instead. I've removed this little lambda function here because it used a string type to represent some graphics. It's actually not relevant to anything we're doing today. I changed the drawing code from drawing white characters to white pixels, and I launched the application using the construct function instead of the construct console function. So let's run it and take a look. Excellent! We can see Game of Life happily fizzing away here. In fact, it's simulating very quickly indeed. On my machine right now, 4,500-ish frames per second of update. It had a boundary condition which stopped it from dying. That was more of a bug actually, but it kept it alive and made it visually interesting. For today's video, what's quite nice is it's almost exactly the same code as it was 8 years ago, and it still just works fine. The simulation runs very fast because the space being simulated was very small. At the time, it was set to be the same size as the command prompt, which was 160 by 80 characters. Let's make it much bigger now and see what effect that has on performance. Because everywhere in the code is sensitive to the size of the command prompt, all we need to do is change our launch parameters to change the size of the simulation. I'm going to change this to something a little bit more modern. 1280 by 960, and I'm not going to have 8 pixels per screen pixel, I'm just going to have 1-to-1 relationship. Let's take a look. Firstly, what was interesting there before the YouTube compression kicked in is how rubbish RAND was. But secondly, we're almost at 1 megapixel now, and we can see we've dropped down to 30 frames per second. The simulation is still ticking away very nicely, although it's hard to see. Recall that this code was written before we had any of the modern day amenities the channel has become used to, such as panning and zooming. Let's make the simulation even bigger now. Let's have 4 megapixels of space being simulated. This won't fit on one screen. Again, we can see just how rubbish RAND is. Look at all of that repetition there. Anyway, we've talked about that before in the procedurally generating universe video. I'm just going to shrink this screen down so we can kind of see some of it. See, it was well too big for my monitor. There we go. Now, of course, at this resolution, a lot of the data won't be being drawn. But look at that, look at those patterns. I do find that fascinating, completely distracting part of this video. However, the simulation is now running. It's running at 4 megapixels, and we're about 5 frames per second. Let's just put that into perspective. That's literally 4 million cells being simulated 5 times a second. That's quite a lot of simulation. But it also reveals a limitation. As we get bigger, all of those cells require additional computation, so the simulation gets slower. That might be fine if you can leave it overnight to get the results that you want, but it's a little infuriating for casual coders like me. So it goes without saying, we can't simply scale the simulation space to be as big as we want. And so I'm going to rely on a different way to encode the cells that should allow us to have very large simulations indeed. Traditionally, when we simulate a 2D space, we specify an array of a certain size. I'm going to assume it's 0, 0 up here, and in the original simulation, it was 160 by 80. This gave us 12,800 individual pixels. 50 years ago, that would have been one tough simulation to do, but as computer hardware has evolved, it's no longer challenging, and we can actually use much larger sizes as we've just demonstrated, and still maintain reasonable frame rates. And it goes without saying that if we scale this image, then the number of cells also scales too, making the computational challenge much more difficult. Not only do we need memory to represent all of the cells in this space, we then need the compute resources to chew through them all. But understanding the content of this image is important. A cell is, well, a dot. It's a pixel in that image, and it has a state of true or false. If we've got just one cell in our whole image, it has to be more effective to store the x and y coordinates of that cell. And if we had several, then we maintain a container of cells with x and y locations. Reducing a space of information to just where the information is a form of sparse encoding. And we see this quite often in computer science, not just with game-of-life simulations, but also with very large matrix representations. We're relying on the fact that most of the space in our simulation space is empty. Naturally, there's a tipping point. If we had lots and lots of active cells in our image, it might become more efficient to store them all. So sparse encoding isn't necessarily a golden bullet, but if you take something like Game of Life in a huge universe, then most of that universe is indeed empty. And so it makes more sense just to represent the cells that are active at any given time. Game of Life is all about a cell knowing what's going on with its neighbours. So given an active cell that I've got here, we need to check all of the neighbours to see what their state is. We count how many of them are active, and that count then determines whether the cell lives or dies, from overcrowding, loneliness, or reproduction. Now, if we represented our cell as some sort of structure with an x and y coordinate, we could maintain a vector of cells. In fact, we would only need to store the active cells. At first glance, this is great because the vector will grow and shrink as the number of active cells increases or decreases. But fundamentally, there is a problem with this approach. If we know the x and y coordinate of the cell we're currently updating, and we need to interrogate its neighbours by offsetting that x and y accordingly, how do we know if such a cell exists in our vector to understand whether it's active or not? Well, somewhat inconveniently, the only way to do this would be to search through the whole vector every single time, and see if a cell with the address matching the description we need exists within it. The standard vector has no built-in locality or any kind of spatial awareness. It also potentially allows duplication of cells, which means some cells could be processed twice. So perhaps we should think a little differently about how we're representing an active cell. Given the state of a cell is binary, it's true or false, then the existence of a cell within the container reflects the state of the cell in the simulation. The only other properties of interest are the cell's location. Therefore, if we had a container of locations, we could perhaps test to see if a specific location exists within the container to tell us whether that cell is active or not. Unfortunately for us, such a container exists. It's called a standard, I'm not going to have enough room here, unordered set. And I'm going to represent the location as an integer XY pair. Using a standard unordered set has some advantages. Firstly, a set is approximately the size of its contents. It will grow and shrink in memory. Secondly, it doesn't allow duplicates. And thirdly, we don't need to do an iterative search to determine if a specific location is stored within the set. Unordered sets use a hash of the thing they are storing to determine where it should be stored within its internal structures. It's unordered, we don't have any control over that. But it does mean we can determine relatively quickly the presence of a location within our set of active cells, which in turn means that specific cell is indeed active. This means we can check a cell's neighbour activity by using the contains function, passing in the address of a cell and some XY offset as required. If this returns true, then the neighbour exists and is active. Now I know that there are some container and C++ aficionados out there that will perhaps pull their nose up a little bit at the standard unordered set approach. There are faster implementations than that usually provided by the compiler vendors. However, I'm sticking with it for this example because if somebody wanted to try along, it's ubiquitous and it's ready and it's included with your compiler. Let's look at implementing this now by modifying the original code. We can see here the two fundamental states of the cell in the previous simulation. They were simply arrays. We're now going to represent the state of a cell by its existence within a set of active cells. Firstly, I'll need to include unordered set. Secondly, my unordered set doesn't know how to hash an OLC vi2d structure. This is an integer 2D location. It's a 32-bit integer as well, so even though I've been saying everything is infinite, the reality is our simulation is about 4 billion by 4 billion cells. To tell an unordered set how to hash something, you need to provide a little hashing function. I'm calling mine hash OLC vi2d, and I'm going to declare that up here. To provide a hash, we overload the cast operator for our specific type. Now, a vi2d consists of an x and a y coordinate. Hashing that is very simple indeed, because I'm going to take my two 32-bit elements and cast them to a 64-bit element, which means all I need to do is stack them side by side in memory. This is convenient, because it guarantees I'll never have any hash collisions for given values of location. It's also computationally very simple, so hopefully nice and speedy. Many times throughout the computation of the game of life, I'm going to need to know if a particular location is active or not. So I'm going to create a little function called getCellState, which takes in a 2D location and checks to see if the set contains that location. Instead of using booleans true and false, I'm going to use numerics here. That's staying in line with how we did the actual game of life implementation down below. Since we're no longer using state arrays, all of this initialization code can go. And previously, we would iterate through every single cell within that state space and update it. We're not going to be doing that anymore either. We're not even going to be drawing them based on their existence within the array. So basically, all of this code can go too. Well, that doesn't leave us with very much now, does it? But I think the removal of all of the existing code just underlines how moving from a state-based implementation to a sparse-based implementation is fundamentally different. and requires a fundamentally different way of thinking. Firstly, I'm only going to simulate anything if I'm holding down the spacebar. Recall in the previous video that we had two states for each cell, its current state and its output. In theory, that's considered its next state. This is because we have to update all of the cells together in one epoch. We need to do the same here, so even though we're not storing all of the cells in an array, we are storing them in our set. So I'm going to have an additional set called active next, which represents all of the cells that are going to be active in the next epoch. Therefore, at the start of the simulation of this epoch, I'm going to set all of my active cells to those that were considered active in the next epoch. Then I'm going to do a little bit of set optimization. Since this run through of the simulation will set active next cells, I'm going to clear that set. But then I'm going to reserve memory for it of approximately the same size as our set of active cells. This might help because typically there isn't a large change between the number of cells per epoch, and it will help reduce the number of dynamic allocations that the set implements behind the scenes. If a cell exists in our set of active cells, or comes into existence, then it will naturally affect the cells around it. It has the potential to change the state of those cells. Another way to think about this is, how does this cell know that this cell exists? This cell is not currently in any set at all. It doesn't exist, and therefore can't possibly partake in any future computations. We need a set of cells that have the potential to change in the next epoch. And conveniently, if we know which cells have the potential to change, then they are the only cells that need to be computed. I'm actually going to introduce two new sets, set potential and set potential next, where set potential is a set of all of the locations that have the potential for change in this epoch. Just as we did with set active, I need to update set potential to set potential next at the start of this simulation epoch. Now, instead of clearing set potential next, I'm going to set it to the active set of cells, because we know that all active cells in this epoch can potentially stimulate change in the next. So now I have a set of all the locations that I need to evaluate for this round of simulation. Let's create a little auto for loop to iterate through all of the locations in that set. And here is where we see our first major reduction in compute resource requirement. Because now we're only going to look at the locations in the simulation space where there are active cells or there is the potential for change this epoch. Just as we did in the first version, I'm now going to count the number of active cells by calling our getCellState function with the location. This will be immediately hashed and the container will yield whether it exists within it or not. Now let's implement the rules of Conway's game of life. If the current cell is active, we're going to do one thing, and if it's dead, we're going to do something else. Why would we have a dead cell in this set? Well, don't forget, this set potential is not just the active cells, it's also all of the cells that have the potential to change. So let's start with the dead state first. The rules suggest that if a dead cell has 3 neighbours, then the cell becomes active, or else the cell remains dead. If the cell remains dead, then we don't need to do anything at all. However, if those 3 neighbours got it on and produced a new cell, then we need to insert it into our set of active in the next epoch cells. A new cell has been born. As a new cell comes into existence, it has the potential to change its neighbouring cells. So I'm going to have a little tiny nested for loop here that just goes around the immediate neighbours of the cell and inserts those into the potential next set. If these locations already existed within the set, it doesn't matter because the set doesn't allow duplicates. Now, if the cell is already alive, it can die from loneliness or overcrowding. But if it's got 2 or 3 neighbours, it's quite happy and lives on. So in the event of the cell being unhappy, the cell needs to die. That means it doesn't make it into the set of active next epoch cells. Cell death is a change, however, so we need to tell the neighbours of that cell that potentially they're going to change. This is the same as this little loop below. If the cell was happy and wants to live on, then we just simply insert its location into the set of next cells. Fundamentally, we now have two important sets that tell us what to do next. We have the set of all of the active cells in the next epoch, and we have the set of all of the locations in the simulation space we need to check to see if they're going to become active or die or affect their neighbours in any way, shape or form. You can see that in the next round of simulation, you can see that potential next gets set to the current potential loop we're about to scroll through, and therefore all of those cells get updated. Fundamentally, we are only performing computation where we need to do computation. Once we've finished the simulation, the next thing to do is draw the set of active cells on the screen. Well, the set of active cells is just a set of locations. So we'll draw a white pixel in all of those locations in the set. We'll have to clear the screen first. Fundamentally, the rules of Game of Life have not changed, but the implementation of state and epoch management is significantly different. We have still got something missing, however, and that is we can't inject any stimulus into the simulation. I'm going to add some mouse sensitivity, that if we are holding down, in this case, the left mouse button, we get the location of the cursor on the screen, and we insert into both sets of activity that location. The reason I'm doing it in both is because I want to draw where we've just inserted new cells, but I want the simulation to also take that into account. Because we've inserted some new cells, we also need to insert the potential for change in the locations of that cell's neighbour. One final change to make is launching the simulation. Let's just make it a bit more manageable right now. I'm going to go with the one lone coder classic 256 by 240 with 4 by 4 pixels. Let's take a look. Well, a blank screen. And as you can see, I can click and draw pixels at the mouse location. And if I hold down space, well, they all disappeared. That's simply because there was nothing there that satisfied going to the next round. Let's draw a bit more of an interesting shape. Oh, blam, really quick. Okay. Well, it looks like Game of Life is actually working quite well. We can play with this. Let's draw the pentomino. I'm sure I'm pronouncing that incorrectly. Oh, I've drawn it wrong already. Let's try again. Up here. That one, then that one, then that one, then that one. Ready? Boom. Look at that. All of that activity from such a small stimulus. We can see we've got traditional Game of Life things in here. There's only so many that represent stable states. These ones are oscillators that flick between one state and the other. You can start to upset some of these by drawing in real time. There we go. Game of Life happening very, very quickly indeed. The problem is we're limited to what we can see. Even though the Game of Life we can see quite happily, it's throwing off all of these streamers in random directions. They're still in existence, of course. They're somewhere else in our simulation space. So I'm going to add a Pixel Game Engine trick to allow us to explore that space with panning and zooming. And this is really just 2 or 3 lines of code. Now, in Pixel Game Engine 2, you can pull in an extension called a transformed view. I will lay down the gauntlet now and say that in Pixel Game Engine 3, this is all fundamentally built in, but we'll leave it at that. We'll need an instance of a transformed view. I call that TV. And I'm going to initialize the TV in onUserCreate to be the size of the screen. In our onUserUpdate function, every single frame I'm going to call transform view, handle, pan and zoom. When we call the get mouse position, that's in screen space. We now want to convert that to world space according to our transformed view. So I'm going to call the screen to world function to convert that. Now, this is where things get a little bit tricky and does highlight a limitation of this approach when visualizing Game of Life. The draw function draws a single pixel in what is effectively a sprite, and that sprite is drawn to the screen. We now effectively have an infinitely large sprite, which of course we can't have. So instead of drawing a pixel, I'm going to draw a small rectangle instead. This is also required because the zooming will change from a single pixel to quite a number of pixels depending on the zoom level. To keep this optimal, I'm going to change a couple of things. Firstly, I'm going to see if a rectangle is visible within the transformed view at the location of the cell, with a nominal width of 1 by 1. What that means is at zoom level 1, our cell is 1 pixel by 1 pixel. This changes automatically by the transformed view. If the cell is visible, then I'm going to draw using the GPU, a rectangle, scaled and transformed by the transformed view at the cell's location. Since I'm now drawing everything using decals and on the GPU, they will disappear every frame, so I don't need to clear the screen. That will save us some important CPU cycles. You may have noticed this draw count variable. Well, I'm using that to keep track of how many things I'm drawing on the screen at any one time, because I'm also going to display some useful metrics just to see how things are going. So I'm going to draw string detail, how many active cells out of how many in the potential set and how many are actually drawn. And let's take a look. So I've zoomed in a little bit and I'm clicking. There we go. So we've got one active cell, but that one active cell has the potential to change 9 neighbors, including itself. So that 3x3 region around the cell. If I change this now into the, oh, I've done it again, haven't I? The R pentonimo shape, I'll just disappear. Let's try that again. There we go, that one. And do a bit of simulation. Well, you can see it exploded with growth. I can use the mouse wheel to change the zoom and pan. There we go. And it threw out those streamers, which just keep going and going and going. We can see that the amount of activity has now become stable. And so every epoch of simulation, there are 116 active cells, but there are potentially 284 that can change. Let's add some interference for these two. Oh, it missed. Let's try again. With my single mouse clicks and drawing like this, I can't cause enough immediate damage. They look like they're effectively disappearing, because as I draw a line here, as we zoom in, we can actually see that most of them just exist in isolation, which means they'll get lonely and then die on the next iteration. We can help with this by moving to a higher resolution and using a 1:1 pixel ratio. Now when I draw a line and zoom in, it is indeed a line, so let's simulate that. Try again, try and draw a straight line as possible. There we go. Now I've got a little streamer going off here, so let's run some interference against this thing. So now you can start to see still lots of empty space there. Oh, it actually shot right through them. The second one didn't though. That's good. Lots of activity going on. Now those streamers will just go off into space. Look at that. Because having my infinitesimally small mouse cursor in an infinite universe makes it very difficult to stimulate the cells conveniently, I'm going to add a much big splodgier paintbrush to do things with. That's the last bit of code to add. In pretty much the same code for the left mouse button, I'm going to add some sensitivity to the right mouse button, but this time it draws a 100 by 100 rectangle of randomly generated cells. This allows me to add a lot more stimulation into the system. So if I right click, there we go. That looks like all the cells have been filled up. I'm going to start the simulation and look at that. Isn't that very nice? Very pretty. And we can draw them like that. Much nicer. Can zoom right in. Let's zoom right back out. And because we're not really limited by space anymore, we can do some simulation up here this time. Now the frame rate does take a hit. It is now entirely based on how much activity there might be per epoch, and also the overhead of drawing all of these thousands of rectangles per frame. As the cells die off and leave lots of empty space behind, there's no residual computation that needs to be performed. It's quite nice that way that the algorithm is sort of self-organizing itself in terms of what to do next. It'd be really cool to do some very, very large simulations like this. But before we can start thinking about very large simulations, we have to address the elephant in the room. At the start of this video, I showed a 1 megapixel image being simulated. That was a whole 1 million Game of Life cells being updated at 30 frames per second. Here we can see we've only got 9,000 cells active and we're running at 38 frames per second. So yes, whilst the simulation can be unfathomably large, we're actually paying quite a lot of performance penalty to have that size. What could be the cause of this? Well, it's more than likely a fairly sloppy implementation of the unordered set. We're doing a lot of memory manipulations, insertions and extractions, and then moving memory around as part of our process in order to represent this location-free state space. We're also relying on a single core to do absolutely everything. Now, because I know some of you will be curious, I did have a look at how you could go about making this multi-threaded to get even more performance out of it, and it does kind of work, although the results are not as satisfactory as I would have hoped. I threw in the quick and dirty OMP or OpenMP parallelization library for C++. It actually makes going through loops very CUDA-like, is that you can tell the compiler to automatically generate a bunch of threads to execute portions of this loop in parallel, and the loop is exactly what we've just had before. To manage that, the sets needed to be broken up slightly. Because the algorithm is fundamentally data reading, that's okay, we're not going to get lots of clashes, but we do need to output the next Epoch set without collisions. So each thread by OMP goes away and does that by using this thread identity value in an array of sets, and at the end of the algorithm the sets are all merged together. However, this merging operation is quite time consuming and in fact makes all of this process a little bit redundant. I've not given up on this, however, and I'm going to explore it a bit further. And so there you have it, Conway's Game of Life, but with a pretty much infinite simulation space. I think it's very fascinating, and I know that there are some very large Conway Game of Life models out there which would be interesting to import and simulate using this tool. Now, I know there's not been that many videos this year, and I've got a reason for that, and that's coming up in a little review video shortly, because we've also got the One Lone Coder Jam coming up towards the end of August too. But as usual, if you've enjoyed this video, a big thumbs up please, have a think about subscribing, come and have a chat on the Discord, all us nerds are still there, and I'll see you next time. Take care.